Good day and good morning, everyone. Uh, my name is Tony, and I will be I'm a course advisor, and I will be your host for today's session. Before we start, I'd like just to give out some housekeeping rules so that everyone get the most out of this session. So this is the notification and sound settings. You are able to turn on and off the notification as you please during this webinar. And please do post any questions under the Q&A function at the top right-hand corner. If the questions are related or they are technical questions, our presenter for the day will be able to assist with that. But if the questions are more general questions, course related, I can be able to answer those. So just some of the frequently asked questions. Everyone registered for this webinar will receive a copy of a PDF slides and a link to the video recording within the next 2 business days via an email. So please do check your junk folder, spam folder, if the email does not appear in your inbox. And we also provide you a free digital certificate of attendance for live attendees. There will be a link and a QR code to short survey provided at the end of the session. So please do stay with us until the end of the session to qualify for the certificate of attendance. Event conduct, please keep discussion lawful and respectful. Follow the chair and moderator's direction. Do not share illegal, abusive, or extremist content. Recording is not permitted unless authorized. Breach may result in removal and referral under the ECT policy. Today's topic is the consequences of overlooking metal additive manufacturing, and the presenter for the day is Dr. Hassan, who is also a lecturer at EIT. Dr. Hassan, you can take over the slides.
Okay, do you hear me well?
Yes, I can hear you.
Very good. Thank you very much for having me today. And while we have different people across the globe, I hope everyone are having a very good Wednesday. For us, it's about 8 p.m. and for you should be midday almost, or still long way to go to finish this day. But anyways, let's have a look at the topic of additive manufacturing. And basically what we are going to focus on mostly today is on metal additive manufacturing. So I hope everything, no, sorry. I missed the slide. Yep, that's it. Well, just a brief introduction about myself. I have received my PhD on metal additive manufacturing in 2009 in Dallas, Texas, in SMU, and continued in the same field in additive manufacturing in Waterloo University in Canada. Continued my career as a faculty member at Isfahan University of Technology for about 11 years. I co-founded the company and was the engineering manager of the company to develop, design, and manufacture metal 3D printers. We have installed over 30 machines, different places, mostly in medical and aerospace industries and energy industry. I have been technology manager of Aurora Labs, a company based in Western Australia and focusing on developing metal 3D printers. And currently, I am a co-founder and director of eMetal 3D, the company that is based in WA and is focused on providing services to local industries in Australia. And also, I'm a lecturer at EIT. So the agenda of this presentation would be around metal additive manufacturing, classification, materials, benefits, and some case studies that might be useful to different people to understand the real applications of this technology. A quick review of the applications of recent days of metal additive manufacturing. It is not a wrong statement to say almost in any industry you can find applications. Currently, we have pioneers actually on all industries around us who are investing billions of dollars in adopting additive manufacturing. It doesn't mean that they're all at the same level, but it means that most of industries are into finding ways to really adopt the benefits and using this technology. Oil and gas, which has been a very wealthy industry, has invested a lot in this section. Here in Australia, we have companies that are moving toward that quite fast. Mining hasn't been that fast because of the limitations of the systems, but still they are also using some other metal 3D printers that have less limitation for the size and application that they need. Medical industry, which has been one of the pioneers actually of using this technology, aerospace and energy industries, they have all been using the technology quite earlier than any other industry. And I would say general manufacturing industries are now understanding the benefits much more than before and trying to use it more efficiently than ever. Just a quick review of what we're talking about. When we talk about manufacturing, you usually have three ways of manufacturing. So we have material removal, which means we have a bulk material and you start removing the material in order to get to the final shape of the design that we have. And that is like CNC machining and lathe machining, a lot of different machining techniques that we know. Then we have forming, that we have a mold that either by pressure or either the material is molten, we form the material to the final shape or to the semi-final shape. And the third one is the additive manufacturing, which hasn't been really a very new technology comparing to, the concept of that. The humans have been using this technology since ancient time, that they started to build their houses layer by layer. But adopting this way of manufacturing in manufacturing, basically, or industry, has been around 4 decades ago. So we are relatively talking about something new, although it is not really considered new anymore. In some specific cases, there are new advancements that we'll talk about that. AM classification is based on ASTM standard that have been published. I guess the start of that was in 2009, and ASTM decided to divide all additive manufacturing technologies into 7 categories. Although there are a few recent technologies that cannot be necessarily fit in one of these categories, and they probably need to add one more or some justification for those new ones. But almost all the other technologies that we know currently, they are among these 7 main categories. Among these 7, 5 of them have the capability of manufacturing metal parts. So when we talk about metal 3D printing, we should really ask what technology. They are not all the same. So out of 7, 5 is a lot. So not all metal 3D printing technologies are the same, and I have just listed 5 technologies, 5 categories that they can actually produce metal parts. Powder bed fusion, direct energy deposition, material extrusion, material jetting, and binder jetting, they all have the capability of manufacturing metal parts. All right, so do they work all the same? Obviously not. And this slide is quite important to understand the main differences, and that hopefully explains some ambiguities about metal 3D printings that have been in the market which is mostly coming from a commercial way of advertising this technology, not really scientific way. So if you look at this slide, we have two technologies on the left and three on the right. The two on the left are the technologies that can actually make final metal part directly out of the raw material. So there is no need for any post-processing, any sintering or other activities to actually reach the final metal product. On the other hand, the three on the right, they are the technologies that you won't get a metal part unless you get into some middle stages of washing, sintering, or infiltration of other materials. And so to basically increase their strength, remove the excess material, and get to a part that is relatively strong and useful for some applications. So that is the main distinction between the two categories. So on the left side, we have PBF, powder bed fusion, which is the technology that I'm going to talk about that more today. Then we have DED, directed energy deposition. That is a very powerful technology. It has been around probably longer than PBF, but it hasn't been advanced as much as PBF. And the reason for that has been really related to the software advancement that hasn't been fast enough as it was for the powder bed fusion technology. In the powder bed fusion technology, we have two main categories of SLM, selective laser melting, and EBM, electron beam melting, which we are focusing on the SLM technology today. The difference between the two is the left one is basically talking about laser. So there is a bed of powder and laser beam. And the second one, EBM, there is an electron beam instead of laser that melts the powder. So if we put these two aside, the other direct metal manufacturing, which is a DED technology, direct energy deposition, this one may use laser, arc, and it can use powder or wire and other ways to manufacture the part. So that is why they have different names. Lens is a technology that uses laser. WAAM is a technology that uses wire and arc. And that is how this technology is formed. I'm not going to talk about the right-hand side, but basically what they do, all three, is you have a mixture of metal powder in a matrix of a polymer. And what do you do is like the FDM technology that you have a filament that is kind of melted and make the part, you can actually have that happening while the filament has some particles, metal particles in there. So once you have the part printed, that we call it green part, that green part has to go through some sequence of post-processing in order to increase the strength and remove the excess material. And as a result, there are going to be a lot of shrinkage, 20, 30, 40% of shrinkage until we get to a semi-solid material. So all these three are out of the scope of this presentation. So we are going to focus on the left side and specifically on the powder bed fusion technology. Okay, so let's go to the next slide. Yeah, I'm going to show you a quick movie that shows the process in a nutshell, and hopefully that helps you. I'm going to mute the presentation. So like any other 3D printing technology, everything starts with a CAD file. So you may have the CAD file from the CAD software, or you can 3D scan the part and then reverse engineer that. You may need to adjust some dimensions, put some excess material for post-machining and so. Next software is the software that you actually use for designing supports. For reasons similar to the reason that we use support in other technologies, we need to have support material to hold up the overhang areas and make sure the part doesn't fall apart during process. So the software here is used to design the orange part that you see here is support material, and also used for nesting the part on a platform. So what you can see here is basically number of parts sitting side by side, and they are all virtually sliced. So the next step in this process is slicing. What we do is virtually, with a very thin layer thickness, around 60 micron or less, we slice the part, and you actually transform the complexity of the geometry into thin two-dimensional features that are much easier to manufacture and produce than a three-dimensional part. So as you can see in this section of the video, while the scroll is going up and down, you see actually through the part and different layers of that. So basically, that shows where the supports are sitting, how they are acting, and these are the information that are going to transfer into the machine. So this software, the next software, is where you actually define process parameters. What power of laser should be used? What scanning speed should be used? What overlap between the layers are used in order to have the best properties, and much more parameters. So everything is defined, or basically better say to predefine in this software. And as you can see in this video, there are some very fine lines that are basically the track of laser for each part. So as you can see, by moving the scroll up and down, we can see the design of each layer as it was in the previous software. The next step is basically the machine that is going to run here, and we have the laser that is scanning the surface, and a very thin layer of powder is now being melted. What you're watching here is a very high speed of laser beam that is moving over 1000 millimeter per second, and it is melting the stainless steel part, and it is welding that to the previous layer. Once this layer is done, then the coater actually brings another layer of powder. So what you actually don't see here is that this section goes down 60 micron, which is very small, so that's why we don't see that in this resolution. That goes down 60 micron, and the other side, on the right side, actually comes up about the same value, and this coater goes on the right and brings back the powder on the left side. So what happens is next layer starts and laser starts to melt. This process continues thousands of times until the whole part is over. Once everything is done, the part has to cool down because it's obviously very hot. And then we can open the chamber and remove the parts. So what you see here, wherever hasn't been melted still remains as powder. So the powder is taken away, the powder is being sieved and reused. So that is one of the main benefits of this technology that we'll talk about that later. And then the parts that are, the sections that are melted are now formed into the parts. So what you are receiving here is basically what you had designed on the software, and exactly the same shape, the same arrangement, and even the supports that you can see from here, the supports are made through the same material, and they are ready to go to the next stage. While everything here is very automatic and no human involvement, the next stages are basically relatively labor intensive because you have to cut them from the platform. So as you can see, this is a platform, everything has been built on, and then all the parts has to be cut from the platform and goes to next steps of post-processing. It can be some machining or deburring and cleaning the supports and so on. Sometimes you need to have some final inspection. If the geometry is quite complicated and if you want to make sure about the forms and other aspects of the geometry, then you probably need to use a 3D scanner. That is what is being shown here. And in this section, you can apply the inspection software, and you can import the original CAD file with the final 3D scan part. and you can match them and find the sections that are showing some errors and realize whether that is acceptable or not. And that is a relatively full process of printing and inspection of the parts. So that's the color map showing where there are some deviations, which is obviously where we are going to do some post machining and make that part finalized. So I'm going to stop this here and go to the next slide to use our time better. If all right. You may wonder what type of material could be printed. Well, the list is actually increasing. We are not talking about a fixed list. There are a lot of researches going on around the world, and this list has been much shorter, but nowadays it is being a lot more material being included. Now we have this list, as you can see. There are some of them listed here on the steel side, on the nickel alloys and super alloys, aluminum, titanium, copper, even tungsten, and some hard to manufacture materials are now being listed uh, in this list. So this section also shows a similar process. As you can see, the powder here has a very crucial role in how you are dealing with this technology. The powder has been developed and improved very much. I mean, the powder manufacturers, we didn't have this much of powder manufacturer like 10 years ago. Nowadays, we have so many manufacturers, and that's why the price of powder has dropped significantly and the quality has increased as we can imagine. All right, so let's talk a little bit about properties. While we are making the part piece by piece and by very, very small welding process, basically, which is about 100 micron welding width or molten pool, then reaching from that very small feature to very large parts in the order of centimeters and tens of centimeters, you can imagine we have millions of weld beads sitting one side by side. So the question would be, are they really fully dense? Do we have any porosity, any holes inside? And that is the question that has been raised from the early stages of this technology, probably back in early days of 2000, 2002, 3, that they started to practice and see how it works. It was not really that good at the time, but later on, by the invention of fiber lasers and by improving the properties of the powder and process parameters and a lot of effort, nowadays, we are really capable of manufacturing fully dense parts. So when we say fully dense, it is obviously not 100% per se. It is 99.567 and higher, which is considered fully dense because when you compare with similar technologies like casting, let's say, casting is a technology that porosity in there is around 1-2% is very common in there. You understand that 99.5 is really a high number. At the same time, when you look at the cross section, not only you don't find really large or even small pores, you see how the weld beads are sitting side by side. So it is practically the process needs to have a very high stability, and all the parameters should be well tuned so that you don't have any porosity happening among these welding beads. Anyone who has done a little bit of welding knows that how difficult that is in the welding process. But in welding process, if a human is doing that, obviously there are so many things that can change. But in a chamber, everything is under control. The atmosphere, the temperature, the oxygen level, the speed of the laser, the power of the laser, and so on. That is why with the high stability of the parameters, we are able to provide such high quality outcome. You may ask about mechanical properties. That is the question of everyone. what is the mechanical properties? Are we dealing with technology that is making some prototypes just to show, just to, say it is metal, or we are dealing with a technology that can generate parts that are capable of carrying heavy loads? Interestingly enough, for most of the materials that are used in this technology, the strength that you achieve after metal 3D printing is higher and sometimes much higher than the bulk material or the wrought material that you get through other processes. For example, in stainless steel 316, if you know, the round bar of 316, the yield strength is around 220, 230. Rarely it happens to get to 250. But here, you can easily get to 500 and above. The reason for that is we are dealing with a technology and with a process that not only has high quality and low porosity and everything, it also provides a very fine microstructure. So the fine microstructure helps to have higher strength. And at the same time, you may wonder how would be the elongation, because when we talk about high strength, usually we are sacrificing the elongation and the ductility of the material. But this is not the case. That 316, for example, shows over 40% of elongation at the same time, which is a very high value. On the other materials, like even in titanium, by 1200 megapascal of ultimate strength, it provides 10% and higher elongation, which is again a very interesting number for the designers who want to use these technology. All right. Now let's have a look at the benefits of this technology and the title of this presentation: why we shouldn't really ignore the presence of this technology, and if we do, what we are really losing. Metal AM has some very significant benefits that cannot be really ignored. One of the main reasons of using this technology, especially for aerospace, that or any other industries, that weight of the parts and the whole system is very, very critical and provides a lot of cost to the whole system, is less material waste and reducing the cost due to that. There is a parameter called buy to fly ratio, means the total amount of material that you actually have to get as a raw material, and the final part that you use in your application, the ratio of the two, how much material you actually wasted, shows that number. So that number is 1 to 2, sometimes more. So we actually, in some ranges, in aerospace specifically, that want to have everything very light, that number becomes 11 to 1. So it means 11 times more than the final part you have to actually spend on the raw material, or even sometimes can get to 30. But if you're using additive manufacturing, you actually can reduce that number to 2 and less. Means if you want to have a 200 grams, 1 kilogram part, you need at most maybe 2 kilograms of raw material or even less. And that is a very game-changing fact. A direct effect of that would be less carbon footprint. And as we know, carbon footprint has a lot of aspects to consider, from the raw material manufacturing, from the processing, all the transportation and everything. Specifically, because of the raw material and much less waste, that has high effect on the carbon footprint and reducing much less carbon or carbon dioxide. Maybe we are not really in aerospace industry, or maybe you're not really dealing with carbon footprint and so, but definitely as a designer, freedom in design is crucial. You know that if you want to make something complex as this image shows, if you don't use additive manufacturing, how difficult that is to design such a thing. First of all, some features cannot be really manufactured, and you have to have a lot of components and a lot of procedures to make individual parts and then carefully machine them and assemble them so that you can get something similar to this. And that would definitely take a lot of time. Design freedom has been one of the main aspects of this technology that lets the designer to think freely and almost be very creative in what they want to really have on their machines. It is a rapid process. Nowadays, we have printers that would last sometimes months to print. Yeah, it is a fact. 2 weeks, 3 weeks, 1 month, and more. So how we can call them rapid? So the point is, when we talk about rapid production, we should really consider and compare this technology with the other ways of manufacturing the same part. It may be time consuming to print, obviously, tens of hours most of the time, but other ways definitely need much more. And in many cases, that actually they cannot use or they cannot really be compared to this technology. All right. Superior mechanical properties. So as I mentioned in the previous slide, mechanical property is not a sacrificing parameter here. Instead, it is a parameter that you actually can rely on much more than other technologies because of the very unique properties that you can expect from this technology. And this is a tensile test result of 316, if I can read it right, that shows the actual strength and elongation of the part. Weight reduction, well, we just talked about raw material and buy to flow ratio, but not only we are able to reduce the amount of material to make a part, we also can reduce the weight of the parts itself. So by the adoption of cellular structures and by adoption of a lot of computer programs that nowadays are available around us, that we can precisely put the material where exactly needed, not everywhere, then we can actually expect to have much lighter materials. A very wide range of materials. I'm not going to talk about that much more. We already talked about that. There are so many materials in many different applications, I mean, many different alloys that can be used. And just an example, beside the standard materials that we know in the market, there are so many new materials that are being developed that are dedicated and developed for additive manufacturing. What it means is these materials like the CP1, which is developed by Constellium, a company, a French company, this material, it is has the alloy content, which is a little bit different from standard alloys in order to improve some aspects of the aluminum alloy that are interested for using aluminum in, for example, some applications like heat exchangers or corrosive environments. So as you can see, the normal aluminum alloy properties would be shown as this gray section as a normalized property. Then we have the CP1 property as the green one. And as you can see, the properties at some points are stretched to provide better properties unlike corrosive environment or surface finishes or thermal conductivity, which is very important for heat exchangers, for example. And that has been a very successful try on this specific alloy. And I'm just saying that there are so many other alloys being developed for these technologies, which might be a little bit different from the standard materials, but they are providing much better results. Another point about benefits of this technology is topology optimization. When we are talking about AI and generative design nowadays, we should also consider that in the manufacturing field. As we know, using the softwares that we have around us, we are able to define the constraints, we are able to define the loads, and then ask the software to provide the design. So we know that where the constraints are, where the connection points will be. We know that where the load is and what type of loads and from what directions we have. And then we can ask the software to start generating the best shape. And because the software is mostly they're using optimization software, so they start removing the places that are not really carrying the load. Usually what comes out of these designs are very um, generic shapes that are cannot be really manufactured in any other way than additive manufacturing. So as you can see, these examples here, these are some generative design technology designs that are manufactured by additive manufacturing. Another part of another interesting part of this, the benefits of using AM is part consolidation. This is a very nice example of, on the left side, you can see the number of parts that has to be manufactured in conventional method. And on the right side, you see the same part, or the same, they're not the same part, but an additive manufactured part, which has been designed for additive, does the same job, but just single part. Single part means much less tolerances, much less inspection, much less assembly time, and so on. So you just need to have post-processing maybe at some connecting points, and that's it. So that is a huge reduction in production cost and time at the same time. Let's have a look at this, some case studies. So this is a hydraulic manifold, and that is an interesting application of additive manufacturing nowadays on hydraulic systems. So this case was first introduced in 2017 at Lund University. That the project is from Atlas Copco, and they asked redesigning of this manifold, which, as you can see here, is relatively large. It is over 16 kilograms of weight, and the material was 316. It has a lot of ports, vertical, horizontal, and as you know, in the way that they are designed and manufactured, is that you have to drill holes, and sometimes you have to cap the holes when you want to block one way. So all the holes are kind of, all the paths, they are crossing one another in 90 degrees, and a lot of sharp corners and pressure drop and so on, beside the fact that it is 16 kilograms, obviously. So this project was to redesign and weight reduction and better passages for the flow. All right. The first try was done and in 2017, and the outcome was relatively successful. As you can see, this is the outcome, and they designed something. The cost was the design was relatively good, but the cost was not really low enough as they expected. And the reason for that was the design has been done in a way that they had to remove a lot of supports after printing. So these walls that you see here are supports that they are extra and they have to be removed, and removing them by itself takes time and effort again. Then in 2020, they redefined this project and they tried to reduce the supports by changing the print orientation and some other factors. And as you can see, just they used 2% of the previous design supports. And that helped a lot to reduce the overall cost of the process. So just have a look at what happened. So they defined the actual passages and they tried to optimize the galleries. So as you can see, all the vertical, horizontal pipes are changed into nicely and smoothly shaped passages. And then they tried to remove extra parts, extra material and using them to self-support the ports, and also make that strong enough to hold itself, because obviously that's going to take a lot of pressure inside. So just the summary of the outcome, it is interesting to see the 16 kilogram of part was changed to 1.4 kilogram. It's a 91 plus weight reduction, weight reduction. The print time was 24 hours, and even they suggested that it is even possible to go to another material that and even reduce the weight much more, but they decided to keep the material as it was previously designed. So that is the base, actually, that nowadays there are many companies are in hydraulic industry, for example, are using additive manufacturing for their manifold design. Let me share a quick story of this Dr. Alien Smith project that was done by eMetal 3D. We received an order of these microphones. So that has been a microphone of a manufacturer in Western Australia. This is the old version. The old version was outdated because of the manufacturers of these panels and brackets were out of market. So he was looking for a replacement. So he came to us to redesign the whole thing. And this is the final, this is the result. So I'm just going to share with you what happened through this process. So that was the challenges were discontinued production of the frame parts, multiple items to manufacture and purchase, long assembly time, and high shipping weight. So that has been the challenges. So the objective was to integrate integration of multiple parts, weight reduction, ease of assembly, and cost effective. This left picture actually shows different trials. So we started with having a design like this, but they didn't like it. So they asked for straight design. So this is the initial design. Then we tried many experiments to find best parameters for the mesh structure and so on. So everything was tested. Once happy with that, then we tried changing even the support to minimize the print time, and that has been one of the batches of print. So in each print, we are able to print 39 cases of microphone, which is basically 78 parts. And the final design is painted basically into black. And this is what you can see. So the material is aluminum, it is painted. And as you can see, the mesh is so fine that it is the sound and air and everything can go through. And this is the application. It's been used for drum and is very successful. So over 300 of those microphones has been manufactured so far. So that was just a quick example of how a redesign can really help manufacturing a component that used to be manufactured in other ways. So in order to have some time for the questions, I'm going to a little bit speed up this section. So as I talked about that, heat exchangers are one of the main applications of this technology. We know that heat exchangers have been around for centuries, I would say, but the traditional way of manufacturing the exchangers is with a lot of welding and with a lot of plates and putting one to another and a lot of pressure drop throughout the whole process to the whole system. And at the same time, the problem is around the size of the heat exchangers. In order to have enough capacity for the heat exchanger, you need to have a large enough heat exchanger to have this large surface area to dissipate the heat. But by using additive manufacturing, you practically can have large surface area in a confined volume. And that is how we have a lot of efforts on manufacturing high efficiency heat exchangers. And in a race cars, for example, in aerospace industries, in any place that you are dealing with limited space and high heat to be dissipated. in even in electronic industry, in drones, that when they want to dissipate the heat, you should have a very light and also efficient heat exchanger to be able to get rid of the excess heat on the electronic devices. So we have a PWR company in Australia and Hydro in Europe that are manufacturing heat exchangers as a continuous production. And interestingly, the Apple Watch. So you probably have this Apple Watch, and this is the new generation of Apple Watch. Apple probably was the first company that transformed the concept of um, limited production, that was one of the features of additive manufacturing, into volume production for Apple Watch, because millions of these watch have been printed. That was a very interesting move. So this short clip actually shows the printing of the cases of this material. It is out of titanium. Some numbers that actually Apple shows on the website, it says it has 50% less raw material usage. It is 100% aerospace grade recycled titanium, and 400 plus metric tons of raw titanium saves in 2025, which probably they're comparing with the traditional methods of manufacturing. But obviously, there were no way that they could manufacture titanium in traditional ways, because we know that titanium is very, very hard to machine and even harder to cast. But they can actually lightly make very light titanium casing of these watches. All right, just to wrap up, let me just have a very quick touch up on this concept of design for additive manufacturing. After talking about the benefits of manufacturing and additive manufacturing, many people start liking that and start thinking, okay, why not 3D printing? But the problem is we need to understand the concept of design for additive manufacturing. On the left side, do you see a block of aluminum that has some features and probably designed to be CNC machined? If actually the client brings this left part and tells us, okay, I want to do 3D printing on that, we say it doesn't work. It doesn't mean that 3D printing cannot make that, but it means the 3D printing of this part is going to be very expensive, because you have to print a lot of material that are practically useless. That is why the printing of the left part is going to be very expensive. Whereas the right one or the middle one, the printing of the middle or the right one is going to be much cheaper than the CNC of the left one. That is how we need to really think about or rethink about how we used to design parts. And there are some concepts around design for additive manufacturing, which by itself requires a very different and separate presentation. But in short, it means that we need to understand the benefits and limitations of the technology on the aspect ratios, on minimum feature sizes, on minimum wall thicknesses, on minimum hole sizes. We need to understand that minimalist design, specifically on the weight, is very important for additive manufacturing. On CNC machining, that's the exact opposite. Less weight in CNC machining usually means more cost. But in additive manufacturing, it usually means less cost. So don't be afraid of making parts complex in order to reduce the weight. We should also design to improve functionality. If we use the same sharp corners and if we use the same non-optimized channels of fluid in a part in additive manufacturing, then we are really wasting the technology and not really seeing the results. We should start thinking to consolidate parts. We should start thinking to how we can get rid of the assembly procedure, how to get rid of a lot of tolerances and fitting things to one another in order to get to the final part, how we can actually make things all printed in one stage. And that is how we can really get the benefit of the technology and make sure that we are really using that in the best way. So that was my last slide, and I will be happy to take some questions if you have any, or if you have typed any, I don't know.
Okay, thank you very much, Dr. Hassan, for this very informative session. I hope everyone did get the most of this session. We will be concluding just now, and if there are any questions, we'll be taking them on just now. These are some of the upcoming courses or upcoming programs at ICT. On the right-hand side is the dates, and on the left-hand side is the course programs. As you can see, there's bachelor's and also master's, and there are dates when the programs will be starting, which is next year, February. And there's still dates for this. There's still dates for this year also. So for more information, you can just check our website, and our course advisors will then reach out to you. So we do have a professional certificate, a 3 months non-accredited professional certificate of competency delivered by ECT's affiliated institute, EIT, Engineering Institute of Technology. Actually, there is a promotion that is currently running on this particular professional certificates that are offered at EIT. It's only for a limited time. You can save up to £334 on our 3 months online professional certificate delivered, as I've said, by ECT's affiliated institute, EIT. You need to enroll by 30 November this year and pay £599 instead of the usual amount of £933. So I will be sharing the link now on the chat for anyone who is interested in the promotion, taking the advantage basically of the promotion fees. So let me just share it now. On the chat, I've shared it now. You just click on the link and just follow the instructions. So this is the QR code. So you can scan your phone to claim the certificate of attendance for this session. And I'll also be sharing the link with everyone now on the chat. So just bear in mind that it does expire after 48 hours. So just need to claim it today if you can, or tomorrow, the latest, because it will be expiring in the next 48 hours. So let me share the link with everyone on the chat also. So we've come to the Q&A, and I don't see any questions from our attendees. Let me see if there's anything that I missed. Well, it seems like there isn't any questions, Dr. Hassan. Let me see, or let's give it 2 minutes. What do you think? We still have some time now. We can just give you some 2 minutes and ask the attendees to ask questions if they want to. And if in the next 2 minutes we don't receive anything from the attendees, which means everything was clear and they don't have any questions, then we'll just close it then. What do you think, Doctor?
Sure. What time is it there?
It's in the afternoon. It's 7 minutes to 3.
Okay.
It's in the afternoon this side.
All right.
Yes. And then what time is it by your side?
It is 7 minutes to 9, basically.
Evening or morning?
No, evening.
Evening. Oh, wow,
Yeah.
wow. It's too.
We're almost
I'm
finishing Wednesday. Yeah.
Wow, 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 wow. Okay. Yeah, I think if nothing comes up in the next 1 minute, because we gave them 2, then we will then be okay. I think there's one question. I'm not sure if you can see it.
Yes. Ashley has asked, can you comment on the use of topology optimized design techniques for parts manufacturer using metal 3D printing challenges and concerns? Well, topology optimization has been around for a really long time, and in the past, topology optimization hasn't been really used very efficiently because it has always been limited by the available manufacturing methods. Since additive manufacturing has much less restrictions on manufacturing side, then that has improved a lot. So there are different softwares. There are many finite element softwares that you can actually adopt for topology optimization. Even the topology optimization has been embedded in many CAD softwares, and they have these features of adding loads and constraints, and they start to use the same concept numerical method to reduce the weight of the part to optimize the design. But we should always think about some aspects that might be missed. And that question probably is addressing those challenges. When we start optimizing a part based on just loads, for example, the usual or the normal way of optimizing the part is based on static loading, for example. So when you use static loading, then you find the stress field and it starts removing the sections that doesn't carry much load, and then redo that, and then you continue until you get to some final feature. At the same time, we should always ask ourselves whether this design is enough for the actual application. Because when you think about fatigue properties, for example, or when you think about some aspects of fracture mechanics, let's say, and some other facts that may not be considered throughout those optimization process, then the outcome has to be really reassessed to make sure everything is under control. So practically, or in summary, I would say that is a very good way of using. I mean, the softwares are very capable of doing that, but any designer should double check and double think twice, basically, to make sure that the final design is really capable to handle the load in the real application. And the reason I say that, because in many other, in the traditional ways, when you're using the actual bulky part, in many ways, it is basically very over designed. So it is practically some concerns are less in there. And when you're dealing with a optimized design, then you have to really careful about all aspects of that. So it needs a bit more concern regarding the simulation process and some more advanced checking on that. But beside that, that is definitely one way to go.
Thank you very much, Dr. And I hope it does answer the question, and hopefully the attendee or the student is, oh yeah, there's actually then giving thumbs up, which means it was well answered. We are at the end of the session. I've shared everything with you. Just please bear in mind that 48 hours, the certificate of attendance link will be expiring. So please do it within the next 48 hours. And this is our contact details, respectively. You can just visit our website. There's our head offices, our contact details also, they're there. So just you can inquire on our website, and the course advisors will then reach out to you if you have any questions regarding our programs or anything for that matter that is related to ECT. Any last words from you, Dr. Hassan?
No, thank you very much and have a good day.
No. Thank you very much, and thanks to all the attendees for taking their time to join us for this session. And you have a good night, Dr. Hassan. By the way,
Thank you.
thank
Yeah,
you. See you on the
thank
next
you.
one.
See ya. Bye-bye.
Bye bye.